All right, let's talk about an algorithm that's an absolute rock star in computer science, binary search. On the surface, it seems so simple, so elegant. But what if I told you it was hiding a tiny, disastrous bug for 60 years right under everyone's noses? So picture this. You've got a digital list with a billion entries, all sorted perfectly. You need to find just one of them. You could start at the very beginning and just check every single one, but you're going to be there all day. There's got to be a better way, right? And of course there is. The answer is this beautiful algorithm called binary search. For any of you who've dabbled in programming, this is like one of the first clever tricks you learn. It's famous, it's fast, and it really seems just about perfect. But here's the kicker. What if that perfect algorithm was actually broken for most of its life? I mean, even the legendary programmer John Bentley admitted his own version was wrong for 20 years. As the slide says, it took 60 years to get this code right. So how on earth could something so fundamental be wrong for so long? Well, to understand the bug, we first have to appreciate the genius of the algorithm itself. It all comes down to a powerful strategy that you've probably heard of: divide and conquer. So what is binary search, really? The key ideas here are sorted array and dividing in half. That first part, the fact that the list is already sorted, is the absolute secret sauce. It's what lets you do the second part. You're not just guessing, you're using the order to eliminate massive chunks of data with every single step. And this is the basic game plan. You jump right into the middle of the list and you ask a simple question. Is my target here? If it is, awesome, you're done. If it's not, is the number I'm looking for bigger or smaller than this middle one? And because everything's sorted, you instantly know which half of the list to throw away. Boom, just like that, half your work is gone, in one step. So really, it's just this simple loop. You find the middle, you make a comparison, you eliminate half the problem, and then you just do it again. You keep slicing the search space in half, over and over, until you've either cornered your number or you've proven it's not there at all. All right, enough with the theory. Let's see this thing in action. We're going to try to find the number 17 in this sorted list you see right here. Let's walk through it. Okay, step 1. We're looking at the whole list from index 0 to 19. The middle is at index 9, and the number there is 10. We're looking for 17. Well, 17 is definitely bigger than 10, right? So we know with 100% certainty that our number can't be anywhere in that first half. We can just toss all of those numbers out. Now we're only looking at what's left, the right half. Find the new middle. That's index 14, which has the value 14. Nope, still too small. So we do it again. We know our target has to be to the right of this spot. We are really narrowing it down now. The middle of this section is index 17, and the value there is 19. Whoa, wait a second. For the first time, our middle number is bigger than our target of 17. That means we've overshot it. So our number must be hiding in that little sliver to the left. And look at that. Our search space is now tiny, just 2 potential spots. We check the new middle, which is index 15, and what's there? It's 17. We got it. And that took, what, just 4 comparisons to find one number in a list of 20. Pretty amazing. So that felt fast, but I really want you to understand just how mind-blowingly fast this approach is when you scale it up. And to do that, we need to talk about something in computer science called logarithmic time. Let's compare it to the simple, brute force way, linear search. That's where you just check every item one by one. We call it speed O of n because the time it takes grows in a straight line with n, the number of items. But binary search is O of log n. And that little log makes a world of difference. It means as the list gets gigantic, the number of steps barely even budges. And if you don't believe me, just look at these numbers. To find one item in a list of 1,000, linear search could take up to 1,000 checks. Binary search, just 10. A million items, that's a million checks versus 20. Now for the big one, a billion items. Linear search could take a billion checks. Binary search will find it in about 30. That's not just a small difference, that's a completely different universe of speed. And this isn't just some textbook theory. This is real-world stuff. A study that used binary search on traffic data for a toll road website in Indonesia found the average search took just over 24 milliseconds. That is literally faster than you can blink. So it's brilliant, it's ridiculously fast, it's basically magic. So how could it have been broken? It's time to go back to that 60-year-old bug that was hiding in plain sight. Okay, here it is, the scene of the crime. The code on the left is how pretty much everyone learned to write this. It looks totally harmless, right? Mid equals low plus high over 2. But here's the problem. If your array is huge, the index numbers for low and high can get so big that when you add them together, they overflow. The number gets too big for the computer's memory to handle. It wraps around and becomes negative. And then your program tries to find a negative spot in the list, which is impossible, and everything just crashes. The fix on the right does the exact same math, just in a different order, and it completely avoids that massive addition. It's so subtle, but so critical. And the real-world headaches don't even stop there. What happens when you have duplicates in your list? Let's say you've got a whole string of 5s all in a row. A standard binary search will just find one of them and call it a day. But what if you need the index of the very first 5, or the last one? Well, turns out you have to tweak the algorithm just a little bit to handle that too. But look, even with these little wrinkles, let's be clear, binary search is an absolute workhorse. It's running under the hood of so many things we use every single day, from giant databases to the core libraries of our operating systems and, yeah, even that toll road website. Why? Because that O log n speed is just too good to pass up. So, there you have it. We know how to conquer a list with 1 billion items. But I want to leave you with a real head-scratcher. What if the list didn't have an end? What if it was sorted and went on forever? Could you still use this divide and conquer idea to find what you're looking for? Now that is something to chew on.